From the Oregon State University Extension Service, this is Pollination, a podcast that tells the stories of researchers, land managers, and people like you who are making bold strides to improve the health of pollinators. I'm your host, Dr. Adoni Melathopoulos, Associate Professor of Pollinator Health in the Department of Horticulture. I know it was a leap year, and there's theoretically an extra day in February, but it really, this month, just vaporized. And I've been on the move. That kind of explains part of the loss of the month. I was down in California for almond bloom. I had the opportunity to be at the 10th annual bee-vent in Albany, Oregon. We had our Master Melitologist conference. And to top it all off, I was in Calgary, Alberta for the first ever Bee-Tech conference. Bee-Tech is put on by the Canadian Honey Council, and I was able to grab 2 interviews when I was there. And I'm so pleased to bring my second interview, the second one I've done on the podcast, with Courtney MacInnis. Now, Courtney is currently, she's at the end of her PhD at the Department of Biological Sciences at the University of Alberta. But a lot of her research has taken place at this wonderful, it's where I used to work in the National Honeybee Lab in Beaver Lodge, Alberta, with Agriculture and Agri-Food Canada. In this episode, we're going to hear about her fascinating research on a new gut a kind of under-researched gut parasite of adult honeybees, Lotmaria, and its interaction with a known disease of adult honeybees, Nosema ceranae. And it is fascinating what she has found out. It is counterintuitive. It is surprising. It's what good research should be like. So without further ado, let's learn about the mysteries of honeybee gut parasites this week on Pollination. Okay, live from the Deerfoot Casino in Calgary, Alberta. Welcome to Pollination, Courtney.
Thanks, Adoni.
You were just awarded the Canadian Honey Council PhD Greatest PhD Award. I think that was what it was officially called.
Sure.
And you gave a talk as well, and you've been working on this problem for a while. I often think people work on bee diseases, honeybee diseases, and they're the common ones, but you chose an obscure, strange one, Lotmaria. Tell us what Lotmaria is.
Yeah, so Lotmaria is a trypanosmatid parasite, which is a protozoan.
Uh-huh.
So it's one of the first animals, protozoa, first animal. It's the second trypanosome that's been described from honeybees. So back in the 1960s.
Really?
Not Lotmaria, no.
Okay.
No. So the first one was described back in the 1960s. That's
okay.
Crithidium maleficate. And when it was described, the people that first described it found that it didn't really cause any pathology. So nobody really had done any work on it since. And virtually everything that has been labeled as Crithidia from like 1967 onwards to the early 2010s was labeled as Crithidium maleficate, but in all but I think 2 instances it was actually Lotmaria.
Really?
Yeah,
okay.
And Lotmaria was characterized by Ryan Schwartz, Jay Evans, and several other people, but they were actually able to characterize it based on notes from Ruth Lotmar, who saw it in the 1940s.
Let me get this straight. So Ruth Lotmar, the Lotmaria, that's where it comes from?
Yes, Lotmaria is named after Ruth Lotmar.
Okay, so I'm protozoan, so it's small, microscopic.
Yes.
And this is for adult honeybees.
As far as we know, it's for adult honeybees.
Okay.
So, I mean, there are one or two studies where people have, you can like artificially feed Lotmaria to bee larvae.
Yeah.
But I have some reservations about that. It's very easy to contaminate larvae when you do that, especially if you're not cleaning them off before you dissect them.
Oh, for sure. Uh-huh.
And I don't think it's a realistic route of transmission for that parasite. So I would classify it as a parasite of adult honeybees.
Okay. All right. So let's just take that for granted. It is, for all we know, and didn't know much about, it was misclassified or thought as another organism. It's in a honeybee's gut. When does it, do you find it? Tell us a little bit about where it's found. Does every beekeeping is it like ubiquitous everywhere?
Yeah, so it has fairly cosmopolitan distribution. North America, Europe, South America, basically everywhere you look for it, you can kind of find it at this point in time. But because it's kind of so new, not a lot of people are, people screen for Nosema everywhere. But Lotmaria is fairly new, so nobody knows what it does, so they're not really looking for it.
Oh, I guess the other unicellular, non-bacterial bee gut thing, Nosema.
Yes.
So everybody knows about, but this people don't look for it, but when they do look for it, they find it.
Yes.
Okay.
Yeah, and it's much more common than Crothidia maleficae. So I've surveyed a lot of colonies for both Nosema and Lotmaria, and to test for Crothidia, I've never found Crothidia maleficae, but almost always can find Nosema ceranae and Lotmaria.
Now, maybe to start with, for beekeepers who are, we're going to get into what it does, but you can see it the same way that when you're looking for Nosema, you take a gut sample out, you mush
Crush
it
them up.
and then they pop up and they look like, I was looking at the picture, they look like a little sickle cell thing.
Yeah, they're kind of like teardrop shaped. They have a tail. They're about 7.5 microns long.
Yes.
That's the promastigote stage, the swimming stage. They also have a round stage where the flagellum just kind of, or their tail flops back and forth and they don't really move. But yeah, they are about twice as long as a Nosema ceranae spore. They're in the hindgut of the bee generally. And if you're a beekeeper and you're looking to, test your bees for them, you crush your bees the same way you would as Nosema. But a lot of people I know use antifreeze or some sort of alcohol or preservative to squish the bees.
Like you do like you're taking a Varroa sample.
Yeah, you can't do that for the trypanosomes though because they're extracellular. So when you put them in,
they explode.
Yeah, they bust and then
you don't see anything.
Yeah, your bees are clean if you do that.
Okay, so you see these things, and they're in the hindgut. So, what does it do? Do we know? What do we know that it does?
Honestly, not very much.
Okay.
So we know that they live in the hindgut. They prefer to be in the ileum, which is like the bee intestine, and the anterior portion of the rectum near the papillae, which is where they release water back into the hemocoel. And we do know that they have the ability to attach to the honeybee gut, so you can see some melanization when you have Lotmaria present.
Melanization is like a little scar.
Yeah, like little scar tissue, so you get little brown or black dots. That's interesting. How do they absorb? They absorb nutrients. We don't know if they're obtaining nutrients when they're, clamping down on the gut wall. But yeah, they can absorb nutrients from the bee. What exactly are they using as nutrients? I don't know. They have the ability to use glucose as an energy source, which is kind of strange because most trypanosomes live in glucose-free environments. Like, you think they're often blood parasites. Not a whole lot of glucose in
just
human
protein.
Blood. Yeah. So bees are unique in that bee trypanosomes have the ability to use glucose, but like most other trypanosomes, they're able to use amino acids. Lots of other trypanosomes use proline as an energy source. And fun fact, proline is the most abundant amino acid in lots of different types of pollen. So.
Okay.
Could be
there. It's in the
glucose,
guts.
Could be
the remnants of what's passing through this gut, and it's living on. Okay, so kind of understudied, very understudied critter inside a bee's adult bee's gut, from what we know. And I guess you were interested in seeing its impact on the honeybee's behavior, on its physiology. Tell us a little bit about your approach to. You have, I guess, maybe the thing that you're famous for is you have these adorable pictures of bees that you're feeding them laced
Laced treats.
Yeah, these treats. Well, tell us a little bit about what you do.
Yeah, so I've got like almost 2 graduate degrees in feeding bees small amounts of parasites in sugar water and making them consume it to their own detriment. But I was really kind of interested to see first if the parasite has an effect on bee survival. So I did a cage experiment for that. We looked at if it has an effect on energetic stress. So are bees hungrier when they're fed the parasite?
Ah.
That was also individual bee work, and then the colony experiment where we, fed parasites to bees, put them in colonies, and then we watched them over time to see if their behavior was atypical.
Well, let's start with the beginning. So, does it change your lifespan?
Yes. So, I work with both Nosema ceranae and Lotmaria passim, and the survival curve experiment was really interesting because that was the first thing I did, and you would think, one is a midgut parasite and one is a hindgut parasite. So,
wait a second, let me get this straight. So we have 2 different organisms, Nosemas in the midgut.
Yep.
And then, so they don't share the same space.
No.
So you wouldn't think they would interact.
Yes.
Okay, gotcha.
Yeah, so that was if we give them both parasites, Nosema ceranae lives in the midgut, Lotmaria likes to be in the hindgut. It doesn't seem like they share resources. So bees that are given both should have a really short lifespan because they're supporting 2 parasites.
Gotcha.
But that was actually wrong. So bees that were given only Nosema ceranae had the shortest lifespan, and bees that had both parasites had an improved lifespan. It was slightly longer than Nosema alone.
What?
Yeah. And then Lotmaria by itself, it had an effect on lifespan, but it was not nearly as bad as the mixed infection or Nosema ceranae alone, which kind of suggests that there's something else is going on, like they're immunomodulating or they're using resources differently. So that was the first part.
Okay.
Then that was coupled with the energetic stress experiment where I put bees into McDonald's straws and, watched them respond to different concentrations of sucrose. And we found that...
I was distracted by the McDonald's straw. Why were you putting a bee in a McDonald's straw?
Yeah, so it's like a tiny harness. The McDonald's pop straw is like exactly the right diameter to put a bee in so that, only their head is outside of the straw and you can strap them in with parafilm so you just have access to their antennae.
Okay, so you've got a bee in a straw and their head's sticking out, and what did you do to them?
I had a little sucrose gradient, so different concentrations of sucrose. Bees have taste receptors in their antennae.
Okay.
So we would take the sucrose and, apply it to the bee's antennae, and if the sucrose was good enough for them, if they wanted it, they would extend their proboscis.
Okay.
We record the concentrations that they respond to, and bees that were inoculated with Lotmaria, they responded more frequently to lower concentrations of sucrose, which kind of implies that they're hungrier, that they're a little bit more stressed.
Yeah.
So the end of that experiment was kind of like, well, they might be able to live longer because in the cages they had ad lib access to pollen and sucrose.
Yeah.
So Nosema ceranae lives intracellularly, so it can destroy the midgut tissue.
Yeah.
But Lotmaria, because it's extracellular, so it's just kind of swimming around in the hindgut. If it's got the nutrients it needs, it's not really harming the bee as long as it gets what it needs. That was the short story.
Okay, so you saw an effect, this learning effect with the Nosema, but not with the Lotmaria.
No, with Lotmaria.
Okay, so they're swimming around, and are they taking away the nutrients that would go to the bee? Is that why they were hungrier?
Yes, that's what. That's what we think, anyways.
Okay.
There's very little work done on this, so you kind of are like. You answer one question, but it's a shot in the dark afterwards.
Okay, so we got these two effects that you found in the lab. So the one is that with the combination, it almost like offsets the effect. And then you have these hungrier bees, which seems like a downside for the Lotmaria. What happened when you went to full-size colonies?
Yeah, so at the end of the energetic stress thing, we saw, that's a change in behavior. We want to know, can they change behavior at the colony level? Because in a lot of situations when you see these really big bad effects in cages, it doesn't doesn't translate to the colonies because they're so big. There are so many bees. They don't, if you have 100 infected bees out of 20,000, you're not going to detect the effect of that parasite because they can just absorb it.
Okay.
So we wanted to see what these two actually did in the colonies. So we made nucleus colonies, which they were small 5-frame nukes. I'm just guessing most people that listen to this know what nukes are.
Oh, yeah.
Okay.
Well, yeah. But just in case, if you are new to beekeeping, a nuke is
It's like a small colony.
It's a nucleus colony.
Yeah, nucleus colony.
Okay, all right. So if you made these nukes up.
Yeah. They were painstakingly equalized because we were doing an experiment. The queens in the nukes were sister queens. All of the paint-marked bees, or bees that we were using, belonged to the queens so that we could control for colony effects and colony dynamics.
Okay.
But what we did was we took frames of emerging bees from the colonies. We would paint mark them and inoculate them and then return them back to their nucleus colonies.
Yeah.
And then over time we would watch them to see when they started to forage, what they were foraging on. And then we would collect samples to be able to see what the parasite load was like. And so honeybee age-based division of labor is partially physiologically controlled.
Yeah.
And parasites have the ability to play with that sometimes. So we wanted to see if our parasites were making these bees physiologically advanced for their chronological age. So
if they were aging faster or something like that, which I guess people know from Nosema, that it has this effect when they're infected. They kind of they burn through their lives faster.
Yes.
Yeah. Okay.
Hard and fast, like a rock star. Yeah, so we were basically waiting to see if these bees would start foraging earlier than they normally should. And for bees with both parasites, that is what we found. Honeybees inoculated with both Nosema ceranae and Lotmaria passim had a significantly younger average foraging age than control bees or bees with only Nosema or only Lotmaria. The trend was there for Lotmaria too, but I had trouble, homogeneity of variance was just not there for me, so you can see the trend is basically the same for Lotmaria as the mixed infection, but from a
lot of variability. There's some were foraging, burning through their lives quick, and some were living nice long lives, but it was all over the place.
Yeah.
But when you had the two,
both parasites,
that's kind of odd. So you have the two of them together, then they really go through their lifespan quickly.
Yeah.
Although when you did the cage study,
experiment, it's the opposite.
Fascinating.
It's very strange. Another fascinating thing is in both the cage experiment and the colony experiment, I squashed bees so we could, count the number of each parasite in each bee.
Yeah.
And the trend between the cage experiment and the colony experiment was the same. And that was in the mixed infection bees, parasite density was higher for both parasites than it is for either of them alone. And so actually bees from our colony experiment that were infected with both Nosema and Lotmaria, they had significantly more Nosema spores than Nosema bees alone, and more Lotmaria than Lotmaria bees alone. So it's very strange.
Puzzling phenomena, but I guess must be the wonder of working with a brand new organism or the frustration of working with an organism that's not well defined scientifically.
Yeah, everything is new, but also nothing is there for you.
I suppose when you do handle a problem like that, the trick is to not project too much on your data, really to listen to your data, because these are probably phenomena that are real and not well resolved, and if you try to make it all fit, you're gonna lose.
Yeah. I think that's very true. And also, if we measured survival in colonies, would it mimic what we saw in a cage? Maybe, maybe not, because of the buffering capacity.
Yeah.
So, the strange pattern with the survival in the cage could be purely a cage thing, because they did have, 60% sugar water, whatever they wanted, 25% fancy irradiated Canadian pollen patty, which, when you're in your colony, you're on the streets when you're in the colony. You get
what's
is
given
available,
to you.
Yeah. So it's very strange. But the parasite density thing holds for both. So
Well, I guess the question is, I imagine the beekeepers are listening and they're like, gee, I'm concerned about this, but I don't know what to do. And it seems like, what do you tell beekeepers when they're kind of like, they squash their bee and they see they've got Lotmaria in the sample? What's the advice?
yeah, I mean, honestly, there is no management strategy for Lotmaria right now. Best thing you can do right now is monitor for it, because if you monitor for it and a lot of people start to say that they have this problem, you can probably get more research dollars to look at management strategies for it. It would be interesting to see, though. Lots of people Alberta beekeepers specifically treat Nosema infections with fumagillin B, and that compound works on an enzyme that Lotmaria also has. So it would be interesting to see if you can kill two birds with one stone, essentially. Like, if you treat your colonies for Nosema at label dose,
I suppose taking the colony level study, if managing Nosema will offset the effect of the Lotmaria. Yeah. I guess this is one of the things when you're doing a PhD on something brand new, there's a whole lot of questions left for somebody else.
Yes, there are more questions than answers at this point.
Which is, I think, what the sign of great research.
Sure. Yeah, I have one chapter left, and it's gene expression data, so it's not my favorite data set, and I'm not done with it yet, but it does show that there's separation within the digestive tract of the two parasites, so that's nice that they all hold the same pattern. And I'm not the only person that's found that.
I suppose when you're dealing with something that seems so counterintuitive, having two lines of data evidence point the same way is reassuring.
Yes.
Kind of, you've kind of confirmed it from two directions.
Yeah. But I think the behavior aspect at the colony level is pretty interesting, because now you know that it probably does do something bad for your bees. So,
well, this is fantastic. Congratulations on your award, and we're looking forward to hearing more. We're getting the full story as you finish your PhD.
Yes, we did submit the colony experiment for publication, so hopefully, by this time next year it's out.
Assuredly, it will be in press, and we'll be looking forward to it.
Yeah.
Well, as people probably learned, as the podcast went on, more people came to this location that we're at, bar, and it's gotten noisier. But enjoy and celebrate your award, and thank you for talking with us today.
Yeah, thanks for having me.
Thank you so much for listening. Show notes with links from each episode are available at the website pollinationpodcast.oregonstate.edu. I also love hearing from you, and there's a form at the website where you can pop in and say hello and give me feedback. If you want to support the show, remember to leave a rating on iTunes, Spotify, or whatever podcast mothership you use. And finally, if you have the means and you want to help support my lab's effort to document bee biodiversity in Oregon, visit OregonBeeAtlas.org and follow down to the donate button, where you can make a tax-deductible donation to the Jerry and Judith Paul Native Pollinator Endowment. Every little bit helps. See you next episode.